All right, let's go ahead and get started. I want to welcome you to Unit 13. This is gases, and Clark High School from San Antonio, Texas wants to especially welcome our latest subscribers from Sioux Falls, South Dakota, Roosevelt High School. Good to have you on board. All right, so here we go. Unit 13, gases. So solids and even liquids have particular particles which are tightly bound to one another, okay? That's what makes them solid or liquid. Now, this is not true of gases. Gases have no definite volume and no definite shape because they are fluid and they're compressible. Okay, you can compress them. For example, if you had a strong enough pump, you could compress all the air in our classroom down to the volume of a basketball. This illustrates how you might be able to do that. You just use some kind of a compression device like this right here, some type of a piston, and you're going to be able to use that to compress a gas. Now, that's something you couldn't do if you had a solid or a liquid. I want to talk about the kinetic molecular theory because this is a very important theory when it comes to describing gases. And here's what it says. It's an idea for describing what is known as an ideal gas. Most gases are called real gases because they don't follow one or more of the following postulates of the kinetic molecular theory. So when we say an ideal gas, what we mean is a gas that has certain characteristics. So let's take a look at what we mean by those characteristics. So the first kind of postulate of the kinetic molecular theory is this. First, the particles of a gas are extremely small relative to the container which encloses it. Most of what we call a gas is really just empty space, okay? So when we say a gas, say a gas is filling the room, the gas particles themselves are not filling the room. The gas particles themselves are, according to the kinetic molecular theory, very, very small in comparison to the volume of the entire room, right? So that's the first postulate then of the kinetic molecular theory. Second, there are no attractive or repulsive forces between particles of a gas, okay? So generally speaking, what we're going to see is we're going to see attractive and repulsive forces. But if we think about an ideal gas, there wouldn't be these attractive or repulsive forces. And that's what makes an ideal gas an ideal gas. So that's the second postulate. Let's take a look at postulate number 3. The collision between gas particles are completely elastic. What do we mean by that? Well, when they collide, there's no loss of energy, either potential or kinetic, when collisions occur. In other words, when the particles bang into each other or they bang into the wall, they don't lose energy according to the kinetic molecular theory. They continue to move with the same energy as they had before the collision. So that's the third postulate. Let's take a look at the fourth postulate. It says the particles of a gas are in constant, rapid, random motion. They never stop moving unless the temperature drops to what we would call absolute zero. And I'll talk a lot more about absolute zero a little bit later. But the point is that these particles never stop moving. They're a constant, rapid, random motion. So that's the fourth postulate. Let's take a look at the last one. The Kelvin temperature of the gas is related to the kinetic energy. All right, the Kelvin temperature is related to the kinetic energy. The higher the temperature, the greater the kinetic energy, and vice versa. So that's the last postulate of the kinetic molecular theory, the fifth postulate. Okay, let's move on. So I want to talk about the relationship between temperature. Well, actually, let's talk about conversion of temperature and pressure. Okay, so we know that water freezes at 0 degrees Celsius and it boils at 100 degrees Celsius, right? We've known that since probably 3rd or 4th grade. But to convert from Celsius degrees to Kelvin, just add 273. That's it. That's all you have to do. To go from Celsius to Kelvin, just add 273 degrees. Okay? Now, just a quick note. Every calculation that we will be doing is going to require Kelvin degrees, okay? You can't do any of these calculations with Celsius, so you have to add the 273 if you're given Celsius. So that's the first important thing to keep in mind. Room temperature, the temperature in our room right now, is about 25 degrees Celsius. So if we add 273 to that, we get 298 degrees Kelvin, all right? 298 degrees Kelvin. By the way, I want you to notice just a little it's not a big deal, but I want you to get this right. See where it says C for Celsius and there's a little circle right there? When you have Celsius, you're going to write the little circle, degrees Celsius. But when you have Kelvin, don't write the little circle. Don't draw in that little circle. So it's 298 K. That's it. Don't write 298 degrees K. All right? All right, so to do pressure conversions, we use the following relationships, right? So the following relationships for pressure conversions. So what we're going to do is we're going to say that 1 atmosphere, which is, by the way, the pressure that you're feeling right now, in all likelihood, if you're in San Antonio, Texas, that's about what it's going to be. However, if you're in Denver, Colorado, you're not feeling 1 atmosphere of pressure. You're feeling less than 1 atmosphere of pressure because you're sitting way above sea level. Okay, so you've got less than 1 atmosphere of pressure kind of pushing down on your shoulders right now. Well, 1 atmosphere, I want you to remember, is the same thing as 760 millimeters of mercury as measured by a different device, right? And that's the same thing as 101.325 kilopascals. So we're going to be able to use these conversions interchangeably. So if we need atmospheres or millimeters of mercury or kilopascals, any of those are going to be fine. Okay? So for example, let's just say we have 620 millimeters of mercury. That's the pressure of a system. 620 millimeters of mercury, and I want to know how many atmospheres that represents. How do I do that? Well, we're going to use dimensional analysis. We've been doing that for a long time. You start with what you know, 620 millimeters of mercury over 1, times whatever's on the upper left goes on the lower right. Whatever you want on top, whatever you want is going to go on top. In this case, it's atmospheres. I'm looking for atmospheres. So 1 atmosphere is 760 millimeters of mercury. Look at what's going to happen here and here. Those units are going to cancel out. And then what we're going to do is we're going to divide 620 divided by 760. Do this with me on your calculator. I'm going to redo this calculation on mine. 620 divided by 760, and I get 0.8157. I'm going to round it to 0.82 since I have 2 significant digits in the 620 and I have 2 significant digits in the 760. Okay? So, does that make sense? So we've got 0.82 atmospheres. That's the conversion. So be sure that you can convert pressure easily. Now, there are 3 variables to consider when you're looking at a gas. They are pressure, volume, and temperature. Pressure, volume, and temperature are the 3 most important aspects of a gas. So let's consider what happens to each by thinking about a balloon with a gas that's just helium in it. Okay, so here's the balloon. Okay, maybe there'll be a little string right there, just like that. And the balloon has helium in it, but there's some other gas on the outside. Now, the particles of helium in the balloon are pushing on the inside of the balloon like this, just like that. And the particles on the outside, the air, say, for example, is pushing on the balloon like so. And so the net force is going to determine the diameter of the balloon, right? So the pressure in the balloon is the result of the helium atoms banging into the inside of the balloon. Okay, so the reason that the balloon, the helium balloon, remains inflated, right, has air in it, has a volume to it, is because those helium atoms are banging into the inside of it, pushing the balloon outward like that. Now, it's not going to happen infinitely, it's not going to become infinitely large because the ones on the outside, remember, they're banging on the outside of the balloon like that, right? So it's kind of like an inverse tug of war. Instead of a pull, it's pushing, right? So what happens to the pressure if you increase the temperature, right? Now let's think back to our kinetic molecular theory for this one. The question is, what happens to the pressure if you increase the temperature? The pressure increases since the kinetic energy of the particles is increased. Remember that 5th postulate of the kinetic molecular theory. Pressure, temperature rather, and kinetic energy are related. So if the pressure increases, since the kinetic energy of the particles is increased and therefore bangs in the wall more frequently with greater force. So if you increase the temperature, you're going to increase the volume, okay? And you're going to increase the pressure. Okay? All right, so that's that. Let's move on. So what happens to the volume of a balloon if the pressure remains constant and the temperature is increased? Well, the volume increases since the increased temperature causes the particles to bang into the inside of the wall of the balloon outwardly, and expand the volume of the balloon. Remember, we're at a constant pressure in this problem. And finally, what happens to the volume of the balloon if it's compressed by a pressure from outside the balloon? Well, we said that this was kind of like an inverse tug of war. So if you push on the outside of the balloon, the volume is going to get smaller, right? It's going to get smaller because the volume decreases since the pressure and volume are inversely related. We're going to talk about something called Boyle's law in just a moment. All right, so I think we got some of the basic principles out of the way. So let's look at 3 important gas laws which involve these 3 questions. The first one is Boyle's law. Okay, Boyle stated that the pressure and the volume are inversely related. In other words, if the pressure is increased, the volume is decreased. Well, that kind of makes sense, right? If you take all the air in the room, for example, you could, if you had a big enough pump, compress all the air in our classroom to a volume the size of a basketball, right? Because gases are compressible. Gases are compressible. So Boyle's law states that pressure and volume are inversely related. So that's the first law that we'll discuss, Boyle's law. And we can use the following equation to calculate how pressure and volume are related, and here it is. The relationship is this. Pressure and volume, according to Boyle, is a constant. I'm not sure why it's K instead of C. I think it's because this originated in Germany, and I think they spelled constant with a K in Germany. Not sure about that, so don't quote me on that, but I think that's the reason why. Either that or Robert Boyle was a very poor speller, okay, but it is K. So PV is equal to K. That's a constant. Or we can write it like this. The pressure in the first situation times its volume is equal to the pressure in the second situation times its volume. So the following graph then represents this relationship. It's an inverse relationship. As the pressure increases, the volume decreases, right? As the pressure gets bigger and bigger and bigger, the volume gets smaller and smaller and smaller. So that's this inverse relationship that we see here. All right? Okay, let's move on. Now let's consider another gas law called Charles's law. So we looked at Boyle's law, the relationship between pressure and volume. Now let's look at Charles's law, which is the relationship between temperature and volume. And here's what Charles's law says. Charles's law says the temperature and volume of a gas are directly related, not inversely, directly related. As the temperature increases, the volume increases and vice versa. So let's look at this diagram here. First, we have a low flame, right? So if we have a low flame, what's going to happen to the particles? Well, if it's a low flame, they're going to move around. They're going to bang into the inside of the wall, and certainly they're going to bang up against this piston right here, right, which is a moving piston. It can move up or down, right? But if you increase the temperature, make the flame hotter, these are going to really bang up against the inside of this piston like that. And what's going to happen? Well, the piston is going to move up and the volume is going to increase, right? The volume got bigger because the temperature increased, and the temperature increased because the kinetic energy increased, okay? So see, everything kind of depends on everything else. So Charles's law can be written like this. V1 over T1, in other words, the volume in the first situation over the temperature in the first situation, is equal to the volume in the second situation over the temperature in the second situation. And we'll be using this formula to do calculations involving volume and temperature. I just want to mention, though, that this assumes, Charles's law assumes that pressure remains constant. And this is the law, this is what the law looks like in terms of a graph. It's a direct relationship, right? As the temperature increases, the volume increases linearly, all right? It's a direct relationship. Okay, a direct relationship. And the last one that we want to talk about is Gay-Lussac's law. And this is that there's a direct relationship between temperature and pressure this time. Temperature and pressure. As the temperature increases, the pressure increases. So if you have a balloon and you increase the temperature, the balloon is going to expand. Okay, the balloon is going to expand. So that's Gay-Lussac's law. We'll talk more about that on the next one. So I'll see you then. Thanks. Bye-bye.